Hi there! Welcome once again to the Science Stream Educational Series on Chemistry. In this video, we'll be looking at the second part of our series on electrolysis, the preferential or selective discharge of ions during electrolysis. If you missed the first part of this series, that's the terms and mechanisms of electrolysis, please click on the thumbnail shown above the video to watch it. At the end of this lesson, you should be able to explain how the relative position of ions in the electrochemical series, concentration of ions in the electrolyte, and the nature of electrodes affect the preferential discharge of ions during electrolysis. Do not leave this channel, as we'll be right back after this timeout. Welcome back. First of all, what do you understand by the term preferential discharge or selective discharge of ions? It is the tendency for a set of ions to be favored for discharge over competing ions at the electrode during electrolysis. The first factor to be considered is the relative position of ions in the electrochemical series. Here, ions lower in the series are preferentially discharged to the ones above them, all other factors remaining constant. Let's use the electrolysis of dilute sodium chloride solution, which contains sodium ion, chloride ion, hydrogen ion, and hydroxide ion as a case study. When connected to the power supply, the ions migrate to the oppositely charged electrodes based on the law of electrostatic attraction. At the anode, the chloride and hydroxide ions compete for discharge, but the hydroxide ion is preferentially discharged due to its lower reactivity and position in the electrochemical series. The ease of losing electrons increases down the series for anions as less energy is required by the ions to undergo oxidation or lose electrons. The hydroxide ions undergo oxidation by losing one electron each to form OH radical. Since OH cannot exist on its own, 4 moles of OH will combine to form 2 moles of water and 1 molecule of oxygen gas, as seen in the anodic half equation. At the cathode, the sodium and hydrogen ions compete for discharge. However, the hydrogen ion is always preferentially discharged due to its lower reactivity and position in the electrochemical series. The ease of gaining electrons increases down the series for cations as less energy is required to undergo reduction. The hydrogen ions undergo reduction by gaining 1 electron each to form hydrogen atom. Being a diatomic molecule, 2 hydrogen atoms combine to form a hydrogen gas molecule liberated at the cathode according to the cathodic half equation. To balance the number of moles of electrons transferred, multiply the anodic half equation by 1 and the cathodic half equation by 2. Add the 2 equations to get the overall cell reaction. Next is the concentration of ions in the electrolyte. Here, the ions of higher concentration are preferentially discharged to the ones of lower concentration, provided the distance between them is not wide, say not more than 3 steps. Now, let's use the electrolysis of concentrated sodium chloride solution, also known as brine, as a case study. In brine, sodium ion and chloride ions are of higher concentration than hydrogen ions and hydroxide ions, since there are more salt particles than water particles in the solution. At the anode, the chloride and hydroxide ions compete for discharge, and chloride ion is preferentially discharged due to its higher concentration. The chloride ions undergo oxidation to form chlorine gas, liberated as a greenish-yellow gas at the anode. At the cathode, sodium ion and hydrogen ions compete for discharge, but sodium ion is not discharged despite its higher concentration. This is because its distance from the hydrogen ion in the electrochemical series is too wide or beyond the permitted gap. Hence, the first factor, position of ions in the electrochemical series, overrides. The hydrogen ion therefore undergoes reduction to form the gas at the cathode. Combining the two half equations gives the overall cell reaction. The last factor is the nature of electrodes. Here we will be reclassifying our electrodes based on reactivity into inert and active. An inert electrode is one not part in the electrolytic process. It does not determine the ions discharged at the anode. Examples are graphite and platinum electrodes. Let's use the electrolysis of aqueous copper 2 tetrahydrosulfate 6 solution using graphite electrodes as a case study. The electrolyte contains copper 2 ions, tetrahydrosulfate 6 ions, hydrogen ions, and hydroxide ions. At the anode, tetrahydrosulfate 6 and hydroxide ions compete for discharge, and hydroxide ion is preferentially discharged to form 2 molecules of water and 1 molecule of oxygen gas, as shown in the anodic half equation. Being an inert electrode, the graphite electrode will not have any effect on the electrolytic process. At the cathode, hydrogen and copper 2 ions compete for discharge, and copper 2 ions is preferentially discharged since it is lower in the electrochemical series. Each copper 2 ion undergoes reduction by gaining 2 electrons each to become deposited as copper atoms on the cathode according to the cathodic half equation. Balance the number of moles of electrons transferred by multiplying the anodic half equation by 1 and the cathodic half equation by 2. Add the two equations to get the overall cell reaction. An active electrode is an electrode that processes and influences the ion that can be discharged. Examples are copper anode in copper 2 salt solution and silver anode in silver salt solution. Let's use the electrolysis of aqueous copper 2 tetrasulfate 6 using copper anode as the case study. Our emphasis is on the anode because the cathode does not influence electrolytic reactions since reduction occurs at the cathode. At the anode, tetrasulfate 6 and hydroxide ions compete for discharge, but none of them is discharged. Instead, the copper atoms in the anode undergo oxidation by losing 2 electrons each and forming copper 2 ions in solution as shown in the anodic half equation. At the cathode, the copper 2 ions from the electrolyte gain 2 electrons and become deposited as copper atoms on the cathode. As the copper 2 ions from the electrolyte are being removed, they are immediately replaced by the copper 2 ions produced at the anode. And at the end is just the transfer of atoms from the anode to the cathode as seen in the overall cell reaction. That is all about the preferential discharge of ions during electrolysis. In our next lesson, we'll be looking at the effects of electrolysis on the electrolysis of copper 2 tetrasulfate 6 using inert and active electrodes. Click on the like button and subscribe to our channel to get notified when the video is published. Thanks for watching.